So the definition of a sequence, an infinite sequence is a function whose domain, we said the domain of a function is all the x values, if the function was f of x, right? Possible x values, whose domain is the set of positive integers. Integers are 1, 2, 3, 4, dot, dot, dot. We said positive, so we're starting with 1, right? The terms of the sequence are, we're just going to use variables to represent those terms, a1, a2, a3. If the domain of a function consists of the first n positive integers only, so if it only goes through, let's say we know that it's just going to be 1, 2, 3, 4, then that would be a finite sequence and not infinite like this scenario would be, right? Where you can just go from 1 to infinity. All right, so any questions just about the terms and the definition, and I think as far as sequences themselves making sense, they'll make more sense as we work an example. Yes?
You said the twice on the second to last.
I said the twice. Just to make you guys happy.
Yes, it works. Yes.
I try to give you extra, and you're like, we don't want it. We just want the bare minimum, Miss Roll. Take back that extra D. All right? Fine. All right, thank you. What a way to get your name on the board, Diego. So let's do example 1. And example 1A, specifically, is the one I want to do. It says, write the first 4 terms of the sequence AN equals 3n plus, is it plus 2 or minus 2? Minus 2. Minus 2, all right? So first 4 terms, so we're looking at defining what A1 is, A2 is, A3 is, and A4. And so it's pretty easy. We're using positive integers. We're starting, because there's a 1 here, it means we're going to plug in a 1 for n. So we just say 3 times 1 minus 2 is going to be 1. And 3 times 2 minus 2 is going to be 4. 3 times 3 minus 2 is going to be 7. And then 3 times 4 minus 2 is going to be 10.
So is this just like a function almost?
Like a function, yeah, right. I mean, it is. It's a function, right? But the domain for that function is the positive integers. So we're just plugging in 1, 2, 3, 4, right? So that's pretty straightforward. Any questions about that? Or lose anybody with that concept? All right, let's do one that's a little bit more complicated. This is example 2. And here our sequence is AN equals -1 to the n over 2n minus 1. And they ask us to find first 5 terms. So again, we're just going to say A1 is equal to -1 to the 1, the first power, over 2 to the 1 minus 1. So it's going to be -1 over 1 equals -1. So A1 is just going to be -1. A2 would be -1 raised to the second power. 2 times 2 is 1, so 1 over 4 minus 1 is 3, so just 1/3 for that one, and so on, right? So this one ends up being A3, they tell us is, if we punched it in, we get -1/5, and so on. So you could, I think you guys get the idea, right? Now, they do note in between example 2 and 3 that in order to define the entire sequence, you can't just list a few terms, the first few terms. You can't just say, well, this sequence is -1, 1/3, -1/5, ... and that'd be sufficient. You have to define what the nth term is in order to actually define the sequence, because there are multiple sequences that could have this for its first 3 terms. Okay, so like they give the example that if you had a sequence that looked like this, then it was 1/2 1/4, 1/8, 1/16. That can either be defined by the function, by the sequence 1/2n, or we could use that nth term, so that's what I meant to do. We could say that was the nth term, 1/2n. But these first 4 terms would also correspond to a sequence that had an nth term of this. So if we plugged in our values and used that, we would get the same thing. We'd still get 1/2, 1/4, 1/8, and 1/16 for our first terms. But that's why it's important that you define the nth term to truly define what that sequence is. Okay? Does that make sense to everybody? You have to kind of know the function that you're plugging it into, right? That's what that nth term defines for you. So, in the next example, this is where, like I said, there's no hard, fast set of steps, you know. This is kind of the puzzle aspect of it where you have to sort of figure it out. It says write an expression for the apparent nth term of an of each sequence. So they give us a sequence 1, 3, 5, 7, ... So who wants to take a stab without looking at the book? Who wants to take a stab at telling me the nth term for this particular sequence? If you've looked at the book, just sit this one out. Let's see if someone who hasn't looked at the book can figure it out. So this will make sure we understand the idea of sequences and also see if we can determine that nth term. In other words, what kind of function could I write that's got n in it, where n is my variable that I'm plugging in my positive integers into? And if I start with the number 1 and start plugging it in, it will give me this sequence here. So, you know, when you're looking at something like this, you're trying to figure out things that you know. So what we do notice is that these are all the odd numbers. So there's a difference of 2, right, between each of the terms. So the number 2 is probably going to factor into whatever nth term we come up with. So like if we said 2n, let's say we said that was our nth term. If I plug in a 1 for that, I start with what number? 2, and what would the next number be? 4. And then 4, and then 6. So this looks pretty good, except it starts with 2 instead of 1. So I slap a -1 on here, subtract 1 from the 2n, and now I've got an nth term that will match this sequence here. Does everybody see that? So that's some of the things that you're kind of looking at. You're looking at the difference between the terms. That'll sometimes help you figure out what an nth term might be. You know, like we saw here, there may be different options for you as far as the nth term goes. There's not necessarily one right answer, but you're just supposed to give me an nth term that will work for this particular sequence. All right? Let's see if you can do the next one, which is the harder one. 2, 5, 10, 17, ... So anybody not looking at the book want to take a stab at that one? So when I first looked at this, I was like, oh, okay, so the difference between each of the terms, like there's a difference of 3 here, and then there's a difference of 5 here, and there's a difference of 7 here. So I can see how the difference is starting with the number 3, you know, is all the odd numbers going forward, 3, 5, 7, and so on. So I could, based on that, I could guess what the next term would be. Based on that, what would you think the next term would be?
26.
The next term would be 26, because it would be a difference of 9, right? So that would be accurate. The next term would be 26, but actually with figuring out the nth term, that wasn't particularly helpful when I thought about it that way. What they hoped you would notice here is that each of these numbers is one more than a perfect square. You guys see that? So if we start with positive, if we start with perfect squares, we start with the number 1. If we add 1 to that, we get 2. The next perfect square would be 4. Add 1 to that, you get 5. The next one would be 9. Add 1 to that, you get 10. Right? You guys see that? So if I said, n squared and then added 1 to it, then that works with my 26 that I came up with, right? 5 squared plus 1 gives me 26. So that's why I'm saying these are kind of tough sometimes because there's no hard, fast rule, right? I looked at the difference, which I found a pattern that would help me guess what the next term was, but that was really no benefit figuring out a formula that would accurately represent this sequence. All right, so there should be some homework problems where you get a little practice on that. You recognize some things that are maybe more common, but I don't foresee me giving you anything particularly complicated with recognizing those sequences because I looked at this one and it took me a bit to figure out that that's what was going on here. Any questions? Does that make sense? Does the idea make sense though? The nth term. All right, so let's talk about a recursive sequence. So any guess on what a recursive sequence might mean? What it might involve? Reoccurring? What do you mean by that?
I don't know, it just sounds...
This sounds relevant. So when we talk about a recursive sequence, it's recursive because a term in that sequence will use the value from the previous term. And so that's what makes it recursive. So terms are based on in let me just write that down. In a recursive sequence, terms are based on previous terms. So let's just do an example to see one of those. So they give us a sequence that's defined recursively as follows. They say A1 equals 3, AK equals 2A, K, 2A, get this right, 2A, K minus 1 plus 1, where K is greater than or equal to 2. And they say write the first 5 terms of this sequence, okay? So one thing to note here is that we've used n as our variable in the previous examples, but you don't have to use n. You can use any variables. Just like we can use, we don't have to say f of x, we can say f of n or f of p or whatever. So you can use it as a different variable in there. So here, this particular sequence, the first term is given. The first term is always going to be 3, and we kind of needed that to have a starting place. So when we do A2, we're going to say that means that we're dealing with 2A, 2 minus 1, plus 1. And so what is A2 minus 1? That's 2A1 plus 1. So that points back to this term here. So then it's 2 times 3 plus 1, which is 7. Okay? Did I lose anybody there? Does that make sense? And so similarly, A3 is really 2A, we're just going to go ahead and plug in the 3 here. 3 minus 1 is 2, so it's the A2 term, 2 times the A2 term plus 1. So our A2 term was 7, 7 times 2 is 14, plus 1 is going to be 15. So all of your terms after this first term are going to be dependent on the previous term. That's a recursive sequence. And there's a famous one called the Fibonacci sequence that they list in the in the next example, in the Fibonacci sequence, says that A0 equals 1, A1 equals 1, AK equals AK minus 2 plus AK minus 1. And they note that K is greater than or equal to 2. So notice with this one here, we don't start with A1, we start with A0 for the Fibonacci sequence. And which I think is kind of interesting since our definition specifically said it's the positive integers, but because it's explicitly defined here, then we can say that it starts with, we have to have two terms defined to start with. So what this basically means is that if A0 and A1 are this, and A2 is going to be whatever this value was plus this value here, so A2 is going to be 2. And then A3 takes whatever the value of A2 was and adds it to the value of A1, so 2 plus 1 is going to be 3. A4 takes this and adds it to that, so A4 becomes 5, and so forth. So you're just adding the previous one to the one that was prior to that, and that's the Fibonacci sequence. So these are both examples of recursive sequences. You may see some of those. Make sure you understand that. I have to kind of keep moving along, so I think you guys have that down. Let's talk about factorials. Have you guys seen factorials before? Does that sound familiar? Yeah? I kind of thought you would, but I wasn't positive. So the definition of factorial. Factorial just means that if you see in factorial, I'll just kind of write it quickly. In factorial is represented by this notation, n followed by an exclamation point. So you would read that n factorial. And n is a positive integer again, just like we had with our sequences. So this would be 1 times 2 times 3 times 4 dot dot dot, times n, n minus 1 times n. So it goes for n factorial. You start with 1 and you multiply all those numbers together until you get to n. All those positive integers together. One thing to note is that just by definition, 0 factorial equals 1. All right, so we would think based on this definition here that maybe 0 factorial equals 0, but it doesn't. 0 factorial equals 1. So make sure you know that. They do note that factorials follow the same order of operations as exponents. So just to make sure that you're clear on what that means, if we have 2n factorial, that's different from 2n in parentheses factorial. Just like -1 squared is different from -1 in parentheses squared, right? What's the value of this one?
1.
Huh?
1.
It's -1, because the rule with exponents is it only applies directly to whatever is to the left of it. It doesn't include the negative if it's not in parentheses. So this would still be -1, because we just square the 1. This would basically be the same as negative in the front squared, so we get -1. However, this right here, we're squaring the whole thing, so this is actually -1 times -1, which equals +1, right? So just like that works that way with exponents, when you're dealing with factorials, 2n factorial means 2 times n factorial. So it's 2 times 1 times 2 times 3 dot 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 n minus 1 times n. That would be what 2n factorial is, but parentheses 2n factorial would be equals 1 times 2 times 3 dot dot dot, where 2n would be our last term. Okay? So the parentheses will matter, just like it matters with exponents here. Let's look at example 6. It says write the first 5 terms of a sequence given by an equals 2n over n factorial. And they tell us to begin with n equals 0. So if we're doing the first 5 terms, then a0 is going to we just plug in the 0 for the n. So 2 times 0 over 0 factorial. 0 factorial is what?
1.
Just 1. So it's 0 over 1. In this case, it doesn't matter because it's 0 over 1. So that first term is going to be 0. That is not what they got. Yeah, I'm sorry. I wrote this wrong. This is supposed to be n as an exponent. My bad. So this would be 2 raised to the 0. So it's 1 over 1. So it's 1. And then a to the 1, I'm sorry, a1 would be 2 to the first power over 1 factorial. So that's going to be 2 over 1. So that's going to be 2. This one's 2 squared over 2 factorial, which is 4 over 1 times 2. So it's going to be 2 also. A3 is going to be 2 cubed over 3 factorial. So we got 8 over 1 times 2 times 3. So that's 8 over 6, or 4 over 3. And then finally, the 5th term, even though it ends with 4, we started with a0, so this is actually our 5th term here. So 2 to the 4th over 1 times 2 times 3 times 4, which is going to be 6 times 4, which is 24. What's 2 to the 4th? 2 times 2 is 4, 8, 16. Right? 16 over 24. And so 8 will go in both of those, so this one will be 2/3. Did that make sense to everybody? Could you do that?
Yeah, what happened to the n minus 1 times n?
N minus 1.
For factorials.
Well, n minus 1 just means, like, if n here is 5, n minus 1 is 4. Right? This is just saying that we keep going up and up and up until we hit n. So it's just, if that's the case, if n was 10, if we were doing 10 factorial, it's just saying that we would go 1 times 2 times 3 dot 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 times 9 times 10. You see what I'm saying? It's just making sure you understand that this will be 1 less, since it's an integer, 1 less than what n was. Okay? All right, any questions about factorials? If you understand what factorials mean, then you should be able to also figure out what something like this is. 8 factorial over 2 factorial times 6 factorial. Right? So if you think about writing this out, that means 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 over 1 times 2 times 1 times 2 times 3 times 4 times 5 times 6, right? So we can basically take all of these and cancel it out with all of these. And we get 7 over 8, which is 56, divided by 2. So that's, what, 28? Right? You guys see how that would work? So don't forget, it's very similar to exponents, right? There's definitely a correlation here, just like we have with exponents, and you can cancel out because it's all of them multiplied together. You can do that with factorials as well. And so it should be sort of obvious to you when you've got something like 8 over 6 factorial. We know that this all the way up to 6 is going to be exactly the same. So you should be able to kind of see that you could go ahead and cancel this out and just say that that's whatever comes after 6. It's just going to be 7 times 8. And sort of simplify your work that way. All right, one more concept that we need to discuss, and that is the summation notation. The last few minutes that we've got left. Summation uses the Greek letter sigma. And again, I'm assuming you guys have seen this before. Do you guys agree? You have seen that? And it looks like this, n over the sigma with a I equal some value on the bottom and then some term AI. So this is called summation notation. And it basically means that this right here defines a sequence which is A1 plus A2 plus A3 plus ... all the way to AN. So we started at 1. That was our starting value for I here. And we went all the way to n. We added the terms together. We summed them up. That's what sigma means. Take the sum. We added them all up until we got to n. This is, again, if you end up being in the programming class, this is a concept that you use when you're doing like loops and programming. And so we say I is the index of summation, is what we call that. To define a couple of things here. N is the upper limit of summation. And 1 is the lower limit of summation. Now, there are some properties of sums. Well, first let's do one. Let's just do an example real quick. They give us an example which is the sum goes from 5. I starts with 1 and 3 I. Is that right? Yep. And so they ask us what's the value of this summation. So it would just be, we start with 1, 3 times 1. And we just add, we count all the way up to 5 using integers. Like that. And so doing the math with that, you come up with the number 45. Is that pretty straightforward? Makes sense, right? And they have something a little more complicated in the next one where they say we go up to 8, we've got an n that's going to start with 0, and we say that this is 1 over n factorial, but the process is exactly the same, right? We say 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial, ... We go all the way until we get to 1 over 8 factorial. And then doing the math for that, you get this big, it's actually not a big number because it's a fraction. So it's just 2.72 is what that one turns out to be. Any questions about summations? I always feel like as we get closer to the lunch hour, it's like we're not asking any more questions because we want to go to lunch. I've got one more thing to show you, so seriously. You guys got this? You clear? All right, there are some properties of sums at the bottom of page 574. I'm not going to write those on the board. And so it's just stuff you got to know. Although I was looking through the homework, and I don't think any of the homework problems use these properties. So you can see it there, and there's some proofs on page 632. I don't know if we're going to get to that or not. But at least for right now, it doesn't look like that's going to be relevant to your homework. So I would just glance over it just to make sure you understand what it's saying. But it's not something that you need for this set of homework. But you do need to know about series. So that'll be our last definition that we write on the board. And let's see. For series, definition of series. For the infinite sequence A1, comma A2, comma A3, dot, 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 comma AI, and of course it just keeps going because it's infinite, not plus, dot, dot, dot. Two things to note. The sum of the first n terms is called a finite series, or another term we can use is the partial sum of the sequence. Denoted by A1 plus A2 plus A3 plus dot 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 plus AN equals, and we're going to use our summation notation, n I equals 1 AI. So if we have that infinite sequence and we say we're just going to take the partial sum of that, just looking at the first n terms, we could represent that by this. That really is just kind of restating what we've already done. That shouldn't be any big surprise to you. But that's what we call a series. The sum of all terms in an infinite sequence is called an infinite series. Denoted by, looks exactly the same, except it doesn't stop going, dot, 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 AI, and just keeps going, and so we represent that with our summation notation where I equals 1 at the bottom, AI in the front just like before, but then we have infinity over the sigma instead of a constant number. So I just want to do one quick example and then you can go. So it says for the series, and they give us this series here. I equals 1 to infinity 3 over 10 factorial. They ask us to find the third partial sum, and then the sum of the entire series. So when we say the third partial sum, we just want to make sure that you understand that, the meaning of that type of language. And so what that means we're finding the sum here if we have an upper limit of 3, okay? So we're just finding that, all right? So we say that that is equal to 3 over, wait a minute, what did I do wrong there? 3, this is, what did I do wrong? 3 over 10, that's an I. That's not factorial, that's a power. So sorry about that. So 10 to the first power plus 3 over 10 to the second power plus 3 over 10 to the third power. So that would be the partial sum, the third partial sum. And if we add all that up, converted it to decimals, we would get 0.333. However, if we did this in the way that it's listed here, we did the infinite version of that, we should be able to recognize that there's a pattern here where we have 3 over 10 to the 1 plus 3 over 10 squared plus 3 over 10 cubed plus 3 over 10 to the 4th. And so each time what happens is we've got 0.3 plus 0.03 plus 0.03, 003 plus 0.003 dot dot dot, no zero, another zero, sorry. And so what's going to happen with that is that we're going to get this 0.333, and the 3 is just going to continue to repeat. But we can represent that by a finite number of 1/3. So they just wanted us to do that problem to show to us that an infinite series can still be represented by a finite number, right? You could have a fraction representation that matches that infinite series. All right. Sorry we went a couple minutes over. Any final questions? I'll tell you this. If you don't have any questions, you're free to go. If you've got some questions, please stick around and ask. Take a couple minutes just to make sure that it's clear. Okay? And I will send out the homework. Expect me to hand out a test next week, which will be a take-home test over chapter. What is it? Chapter 7? Yeah, chapter 7. Have a good one.